All right, everybody. So what I did is I went through and provided some commentary on a little bit of the review that we did for review or for exam three. Our actual recording got chopped up, so I wanted to just give you guys sort of a completed version of this, and I thought I'd maybe reformat it so that I can actually walk you through the content a little bit. So this will be sort of broken into sort of about 15, 20 minute conversation about the material that we covered as part of a review on Friday. But yeah, so what I wanted to do is sort of just to recap a little bit about what we talked about, sort of hit on the key points affiliated with the types of problems that you'll be faced with on exam three, that being a take-home exam. So remember that you have everything at your disposal with the exception of primary literature and of course yourselves. You can't work on it together. But with that being said, right, you have all the metabolism sort of notes readily available for you. And so what's going to happen is that your metabolism questions are going to get a little more complicated, such that you're going to be faced with sort of what's under metabolism one here, right? And so you start with a lead compound, and we'll say, okay, that thing went through metabolism and it produced metabolite A and B. Okay, so both of those metabolites are a little more complex than just, let's say, one metabolic process happening, and then it being done right there. So now you're going to have to walk through sort of the steps that are affiliated with the breakdown of the molecule through metabolism. And you'll do that through a combination of sort of your descriptors and enzymes. So for example, right, the P450 doing oxidative dealkylation be a good example, for example, of either oxygens or nitrogens. Or you may be faced with a situation where something can happen spontaneously, such as when you have a free amine in the presence of a ketone, right, that can form an imine. That also exists sort of in equilibrium with the corresponding enamine, right? So anything that can be sort of acid or base catalyzed, remember, can occur because you're in water, right, in the body. And so what I did was I took the first one and sort of walked through step by step, sort of how I would go about doing this. So in the first one, what we see is you have the lead compound, and that goes through metabolism, and you generate metabolites A and B. Okay, so what you want to do in the event that it is split into two, it's not always going to be, but in the event that it is, you probably want to get after dividing that molecule into something that looks pretty close to the molecules that you're going to be breaking it into. And so what you can do is, if you look down the center of the molecule, you have a metabolic transformation that you know of that can break this into two, and that's through an esterase. So if you head to the bottom, now, right, we have the starting lead compound, and after it, approaches an esterase, that can break that carbon-oxygen bond and ultimately perform hydrolysis of that ester. And so what you end up with is sort of the top and the bottom structures right in the middle. But something that you're going to also have to keep in mind as you do this is the structures that you generate, whether or not they're going to be stable as is, right? So not that this is unstable, but you have to keep in mind that sort of the top one is actually a tautomer of the ketone, right? So both of those could be in play as you continue on in sort of the metabolic sequence. Okay, so you have this first breakdown, it generates corresponding alcohol and the carboxylic acid, but then the top molecule can go through tautomerization and it can generate the corresponding ketone. Okay. Now, continuing on, now you have a situation where you have to take sort of the alcohol that you generated at the beginning through that esterase, and you have to take that thing through and it has to turn into metabolite A. Okay, so when you're doing that, what I would do as a strategy is sort of walk around the molecule and say, okay, do I have the right functional group where I need it? Okay. And so, if you just, let's say you were to start with sort of the top left piece there, right? That ketone. Okay. If you start with that, what you're going to have is you're going to notice that ketone becomes an alcohol. Okay. So one thought might be to go ahead and it might be a ketoreductase that reduces that. You can also say alcohol dehydrogenase, but I'll talk about that in just a second. Okay, so then if you continue around, you see now the group on top is actually an alcohol, and that needs to become a ketone. And so how does that happen? Right, that needs to either go through, you can either select a KRAD or an ADH alcohol dehydrogenase, and that's going to do ultimately the oxidation of that alcohol to the ketone. And then finally, you have one more reduction to happen, right? So in the bottom right, you have to reduce that ketone down to the alcohol. And so you can use, once again, a KRAD or an ADH to get you to metabolite A. Okay, so something that's sort of important here, and I would like you guys maybe to practice a little bit, as you're doing this, is sort of those designations, right, for ketoreductase or alcohol dehydrogenase are based on what it's actually doing. That's how they're usually referred to, right? So, for example, the one easy one to remember is the ketoreductase. Ketoreductase is always reducing a ketone. Okay, it's right in the name. Okay, but something that's maybe not as intuitive to you, right, is the alcohol dehydrogenation. Okay, so I don't know if you remember back in the day when you had the reductions of like a alkene in a hydrogenation process. Remember, so we talked about earlier in the class is if the reverse direction, if you were to take an alkane to an alkene, right, that would be a dehydrogenation, okay, or ultimately an oxidation. Okay, so that's where that alcohol dehydrogenation designation comes from. Okay, so you may want to be a little bit more intentional in the exam to say sort of which direction it's going, right? So what I've done is at the top and on the bottom, we have sort of what we went through in the top, but then on the bottom, we have what would be a sort of more specific type of description, right? So that first one, we reduced to ketone, okay? So that would be through a KRAD. The second one, we actually oxidize an alcohol up to a ketone. So that would be an alcohol dehydrogenase. And then finally do a ketone reduction to get to metabolite A. On the exam, I'm not going to be too picky about this, but I think as you get closer to the final, and this is maybe the time to really think about this stuff, as you get closer to the final, I'm going to have sort of the expectation that you're going to, be able to speak about this pretty intelligently. Okay, so this would be the time really to get down sort of all these types of concepts and really be able to describe each of these steps well. Okay. With that being said, I would accept both, but I would like to. It would make me happy, right, to see that you do describe them in the right sort of direction. Then we had to move on to metabolite B. And so what we started with is this compound in the top left. We know if you look at metabolite B all the way at the end here, that what you had to do is you had to take that the NO2 group and you had to shift it over. We only know one way to do that. And conveniently, the other hint is that you had to get a hydroxyl group there. Okay, so in the first step, right, that would be a P450 NIH shift. Okay. The second one, you then have to, before you put an acyl group on that nitrogen, you have to reduce that nitro group down to the amine. Okay, so something to not forget, right, is those P450s, they don't only do oxidations, they also do reductions. So they're going to reduce, so in this case, for example, P450 is going to reduce the NO2, it's going to take it down to the amine, and that sets it up well to go ahead and head through an N-acyl transferase and ultimately an N-acylation of that nitrogen. Okay, so while I'm providing sort of those descriptors at the bottom, the NIH shift, the NO2 reduction, the N-acylation components, is because when you get something a little complex, and I think the ones that you have on your exam are a good for all, I think you have to propose like 4 of them. And I think they're in the neighborhood of like a good 5 or 6 steps for each one. So you're going to want to make sure that you're describing those well so I can follow what you're doing. Make sure that when you do this, that the work is not sort of all over the place. Really take some time, get an extra sheet of paper if you need to discuss it a little bit, because that'll help me, grade and also not put you in a situation where you have maybe the right answer, but I can't really interpret it. Okay. Now, the next stage of that whole thing is I'm gonna ask you, well, hey, this is really great. You rationalize what both the metabolites are, but we need a little more information. You are the medicinal chemist in this scenario. Okay, so I'm going to ask, well, if that thing goes through this metabolic process, we need to increase the half-life without a complete redesign of the molecule. So can you provide some hypotheses, some hypothetical structures that might be good to test that may have sort of similar type of activity, but don't go through that metabolic process? And so, I went through a little bit what we discussed in class. And this is sort of what I sort of came up with. So there's these excellent answers, good answers, and maybe not so good answers. Okay, so I'm just going to go from left to right. So we have left, right, is our original lead. The middle and the top, there's an excellent answer that in order to avoid metabolism of that ester, what you're going to do is you're going to just take out the oxygen. Right? Then it can't go through the esterase, or an esterase isn't going to act on it and hydrolyze that bond. Okay, so that's a great one. Perfectly great. The other option, though, is to go ahead and add some methyls nearby, right? Just from a steric standpoint, you can start to disfavor the ester hydrolysis. And so perfect place to do that would be on the aromatic because it's closest to ketone for one. But then on top of that, it's also sort of just a real convenient place to put it that's not going to introduce stereocenters. And we'll talk about that in just a second. Bottom left, this is another one that was proposed. I would say this is a good answer, but let me tell you what sort of the distinction is there. It's a good answer. So say you put this sort of quaternary carbon that's adjacent to the ester, right? That's definitely going to block off some of the esterase activity because there's sort of a bulky group near it. But the reason why I say it has a little bit of maybe negativity in terms of the sort of the answer is that it does sort of you do perform sort of a significant structure modification, right? So if we were actually designing this to go into the lab and do this, you may have a situation where like you've modified the structure such that you've extended it a little bit, so it might not fit right in the active site, or in the binding site. So this is one I would accept. I would say all these are acceptable except for the last one. But something to think about, right? You want to make minimal changes to the structure, but you also want to address the problem, right? So the top two are good. The one on the left is pretty good. The bottom left is pretty good. But then we have sort of what I would call an okay answer, and this is creative, but I think I put it in sort of the camp of okay. And the reason why is because it is definitely going to prevent hydrolysis, right? You completely remove the ester. And, but you've now made a major, I would say, structure modification, right? You don't have that sort of linkage between these two, right? Whether it be an ester or even if you turn it into a ketone or whatever you did, this is a significant change, right? You brought those two rings pretty close to each other now. So that'd be something I would be a little concerned about. But if you rationalize that well enough, I'm probably going to be pretty okay with that. Now, I tell you guys all the time not to get duped. And the bad answer on the bottom right is going to be the situation that you say, okay, hey, you know what? Look at that top right answer when we added the methyls. Well, why don't we add it on the other ring? Right? It makes perfect sense. Go ahead and do that. Okay, but here's a problem, right? So the methyl that's sort of on the top and that's attached to the alkene is fine, but you have a problem such that you've now added a methyl sort of on the bottom of that ring on the left, and that methyl now represents two structures, so diastereomers. So you've introduced a stereocenter, and the problem for that, for the problem about that, and we've learned that earlier in class, is that you're going to have one that goes towards you and one that goes away from you, and they're going to bind much differently. So you've really proposed two structures there. So you want to propose structures that don't introduce a stereocenter. That's something that I will be looking out for. You'll probably lose half credit on that one in the event that you do that. Okay. But all these, the key here though is that you don't get hung up on there being one particular answer, right? I want to see you guys rationalize them and rationalize them well, right? Again, it doesn't have to be paragraphs, but at least rationalize them such that I know what you're talking about. If you rationalize them pretty well, with a pretty good reason for it, I'm likely not going to, hammer you on points. I wouldn't be too worried about that. Okay, so now we go on to metabolism, the 2 problem. So the second one. Okay, so again, right, this is going to start with something very similar to what we did last time. You're going to have, in this case, right, it's a peptide or an amide that you're going to break apart. And so you're going to use a peptidase to do that. Okay, and that's going to take you get you to the free amine and the sort of carboxylic acid on the right, benzoic acid. Okay. And so, maybe the first one to tackle would be going after, figuring out how to turn that benzoic acid into metabolite B. And so, what you may see and what we've sort of referred to these transformations as is sort of direct oxidations, right, of the aromatic. Okay, and so I think it's important to note, right, you can say, right, oxidation of the aromatic or whatever it is you'd like. Those are both done by P450s to introduce both of those hydroxyl groups. But please remember, right, these are NIH shifts, okay? And that's in the notes. So I would go and look. Now you're gonna go, okay, you're so used to saying, well, no. Well, like chloride, bromide, nitro groups, those are the ones that go through an NIH shift. Well, the mechanism is still the same if you don't have anything like a chloride, bromide, or nitro group. The thing that shifts, though, is going to be just an H, right? So you don't see that in sort of, going from structure to structure. Please keep in mind that it still occurs through an NIH shift. Heading over to rationalization of metabolite A. Okay, you start with 2 sequential N-dealkylations with P450. You guys have plenty of time on this, so what I want you to do is to actually draw it out so it's nice and clear for me. Don't write 2x P450 thing. I just want you to show me what you know. So one step and then do another step just like this. Okay. But now here's sort of the situation where you're going to have to be like, okay, well, now sure, we can have an enzyme act on this, but what you know is that in water, in something that contains protons and a bit of base as well, right? Such that it's water, so you have protons floating around, you have water floating around. You can go ahead and start to do spontaneous processes that I want you to remember, right? And so one of them, and we've talked about this a ton, is imine formation, enamine formation, etc. Okay, so one thing that you should recognize is once you get to the top right structure, that can actually go through spontaneous imine formation. Okay, now I drew the imine directly. Okay, and so what I would say is, just for completion's sake, you may want to draw what that mechanism looks like to get you to the imine, because that is likely going to come up on your final. So take the time to learn that and really get it down, because the quicker it is, sort of second nature to you, the better. Okay. But even if you're there, right, then you have to sit there and go, well, okay, so we made an imine that gets us closer to the structure than we need to, but it's important to remember that that's in equilibrium with the corresponding enamine, which is on the right side of the middle. Okay, those are just tautomers of each other. Okay, now once you get to that tautomer and you're sitting at the enamine, well, those are all in equilibrium with each other. Okay, so nothing is really you can't really drive this thing any further to get to the sort of full-blown aromatic system, right? Unless a P450 comes in, does the oxidation. Okay? And from sort of your previous exam, what you'll know is once you get that sort of that aminol intermediate, that OH can then leave. And then after sort of taking off an H with water, you're left with metabolite A. One thing I didn't mention at the beginning of this one is that you see a stereocenter there, so use that as guide. One thing I would do is label your atoms such that you can follow where everything's going. I recognize that for you guys, like, you don't think about organic chemistry every single day, but this is medicinal chemistry, so you have to think a little bit about sort of how all these bonds do come together in the body, right? So I would think about maybe labeling them right at the beginning. So then okay, right at the beginning that you're gonna have to take off 2 methyls. So those have to leave. And you have the tools to do that, right? With a P450, for example. And then after that, you're like, okay, well, we know ultimately they have to generate sort of a 6-membered ring with the nitrogen. So now you can start to count, right? From the ketone carbon to the nitrogen, you have 6 atoms, right? So that's a good opportunity for you to go ahead and create sort of the 6 structure that you need to. So that one is a really neat problem. Sort of hits all sort of different areas for you guys. The last one I did want to just go through, we didn't get to cover this at all actually during our review, but this is something that I wasn't too worried about you guys figuring it out. But now it's your time again, right, to become the medicinal chemists that I know you can be, right? So you're going to be in a situation where I'm going to say, hey, we got this drug, and we got to come up with a way to sort of start to think about it. Okay, we know this drug binds really well to a particular binding site, but we don't know anything about the binding site. So can we start to hypothesize about a binding site, about what that might look like? So I'm actually going to have you design a binding site, most likely. And so when you do that, you have to think, okay, well, you've seen sort of the ones where I've had you take a molecule and fit it inside of a binding site, but now you're going to do the designing of the binding site. Okay, so you're going to literally draw a circle, and you're going to put on the residues that you think are involved with binding. And so what I've done is given you one of the examples, and naproxen on the top right, on the next slide. So this is something that I would do. And using colors is actually a great way to do this. Some people use like colored pencils. Those are super, super good for doing this type of thing. Right? So you take naproxen, put it in the middle of the circle, and then start to put residues on. And so what you'll see is I've capitalized on sort of the potential, you can call them pi stacking or van der Waals types interactions that are going to occur. So what I wanted to do is I really wanted to hit a van der Waals interaction with that methyl. So I did that with sort of a leucine. But then I also wanted to do sort of a pi stacking type of van der Waals type interaction between sort of the core of the molecule, those 2 aromatics, and tyrosine and a tryptophan. Okay, so that's really cool. But then I wanted to get a little more creative with it and say, okay, well, how do I install something sort of on the bottom right that sort of serves 2 purposes. One, to do to get you the van der Waals interaction, but then also get a hydrogen bonding interaction between an ether on the right and the NH of the next of the sort of indole heterocycle there. I did go ahead and incorporate also a hydrogen bond between the tyrosine hydroxyl group and um, the carbonyl of the acid that's on here. You may say, hey Kyle, there's that OH still hanging out there all the way on the left. And sort of what I put sort of at the bottom of this is it's really gonna depend. What you come up with is really gonna depend on what I ask. So if I say they don't use 3 residues or design one that sort of fits it in pretty well, I'll understand like if you don't use every single interaction on a molecule. But I would say like if I were to throw this into a binding site and it made all these interactions, that thing's gonna stick in there pretty good. So you want to cover at least most of them. If you can cover all of them, that's great. But you don't have to go too crazy. I just want to have some theoretical from you. And on that note, you'll have these all on the module section. I think these will serve as pretty good practice. Feel free to do this for a few more of them that are on there. It'll take you a little bit of time, but it's definitely worth doing. I think at this point, you guys are equipped with what you need to get after some of the problems on here. But I wish you guys the best of luck on exam 3 and looking forward to handing it out on Monday. Thanks so much, everybody.